more or less stable?
Yeah, I'll go ahead and.
Okay. Well, welcome everyone to the January 24th CI Engineering Talk. Our talk today is a redux of a talk that Michael was asked to give again through popular demand. So thank you very much, Michael. And that is on understanding and using segment routing in RNE networking. So Michael, thank you very much for doing this. And the floor is yours.
Yeah, so I'll give a little bit of overview of the purpose of this talk. First of all, I'm a core routing network engineer at ESnet. I've been in ESnet for 14 years, and before that, I worked for UC Berkeley for something around 19 years. So I have a lot of experience in routing, basically. I gave a talk at TechX regarding traffic engineering using segment routing and some things that ESnet is doing. And I had some people come up to me afterward who said, that was a really great talk. I didn't understand any of it, but it was really great. So I wanted to kind of maybe present a little bit of background so that you don't have to just like the talk by the way I deliver it, but you can actually understand some of the words that I use in it. So I was hoping that we could maybe get a little bit more of an understanding of segment routing and how it's used in maybe how you might want to use it in your own network, but also how other networks use it, where you may transfer data between you and other sites over those networks, and trying to understand the technologies they're using to make those transfers work and be as seamless as possible is, I think, a good thing. So hopefully you'll be interested in that. I'm very intimidated by the quality of people who are on this talk right now, who are watching this. So I'm probably going to make some mistakes, so feel free to call me out on that. And I'm definitely a little nervous because of that. So just to let you know. Before your eyes glaze over, because mine always used to glaze over around segment routing. And part of the reason is like the very first question, the very first thing it purported to do is, as a technology, it provided a mechanism for doing source routing. And I was like, well, first of all, I thought that was bad. And secondly, why would you even want to do that? So in this presentation, I hope to answer that last question a little bit more. And also in the next presentation I'm going to give next week, which is a longer traffic engineering talk, I will also try to give some use cases as to why you might want to do this sort of thing. But I also want to talk about like source routing in general. It got a bad rap in the IPv4 days. So if you're as old as I am, you remember when loose source routing in particular was a bad thing in IPv4. And the reason for that is that the way loose source routing was implemented in IPv4 as an options header was it required the return path to be the same as the forward path, which meant that you could spoof an IP address from another network and then force the return traffic to come back through your network. And you could therefore basically hijack or spoof a TCP connection that way. Segment routing doesn't work that way because it's usually held within domains, but more importantly, it only works in one direction. So in order to program a packet in any way, you can only do it in one direction. If you want to do the return direction, you have to go to the other side and program the packet coming back the other way. So that's a really important way to distinguish between the old sort of bad loose source routing of IPv4 and the source routing that segment routing tries to do. How does it actually work? It can be layered on top of existing technology, which is what really I think gives it a real advantage over other mechanisms of sort of network programming and programming packets. We either lay it on top of standard MPLS, sort of basically MPLS encapsulated packets, or we can actually do it in IPv6 using a standard IPv6 extension header. So it's just a type of routing extension header for IPv6, and that's called SRv6. The version that we're looking at is called SR-MPLS. Now, you may think this, or you may have heard people say, oh, it's kind of a form of SD-WAN, and what makes it SD-WAN-y? Essentially, you can use a controller with segment routing and use the offline controller to program packets in ways that are different from the sort of shortest path routing protocol mechanisms, and instead use other mechanisms, including even things like AI and ML to impart logic into the paths that your packets take across the network. So because of that, it does have that sort of controller aspect to it. Now, what makes it different from things like OpenFlow and segment routing, what makes them different. I'll talk about that a lot more in this presentation and in the next presentation that I give next week. But suffice it to say that the biggest difference is that segment routing programs the packet individually rather than programming the network or attempting to program the network. And as a result, all of the state, all of the information about how the packet gets from one place to another is already embedded in the packet. You don't put a lot of state in the network. So yeah, SR might be kind of confusing at first. Your eyes might glaze over because we start talking about things like SIDs or segment IDs, and what are all these different SIDs that I have to worry about? Well, what I hope to do in this presentation is really kind of give you sort of the minimalist approach. Like, here is a very basic segment routing configuration that you can put on your network, or you can try to understand this very basic segment routing configuration, or understand how, for example, like other networks are forwarding your packets across, and I'll show some examples of that later. So I don't really like new vocabulary, so I'm only going to tell you the words that you need to know immediately. I'll give you some definitions, but I'll try to touch on and highlight the key ones that are important. So really what I'm trying to do here is kind of give you the 1970s TRS-80, like even before disk drives, like cassette player version of segment routing, and then we're going to work our way up from there. Maybe we'll add a disk, maybe we'll upgrade to the Trash 80 Model 3, like I did in high school. That's how I learned to program in high school. This was my junior high version. My junior high had these old TRS-80 Model 1. So we'll try to get to the Model 3 later, and then we'll move on. But right now, we're just going to start with the baby steps of getting segment routing going. Just a quick disclaimer, I do use a lot of Nokia examples. ESnet's core routing is all Nokia service routers. I almost call them segment routers. So I'm going to give SROS and Nokia examples. I'll try to throw in a few Juniper here and there because I am familiar with that platform. But please note that I'm not endorsing either platform. They're all good. They all have positives and negatives about them. So we do have to do some vocabulary early on, and these are sort of the most important ones that we're going to talk about when we talk about segment routing, and that has to do with the segment identifier. So why do we create a new word for what is essentially an MPLS label? Well, in the case of SR-MPLS, it is an MPLS label, but in the case of SR-V6, it looks more like a V6 address. So the idea here is that segment routing as a standalone technology can be implemented in a variety of ways. And so we create a different word to say, this is the segment identifier. It's a concept that exists outside of MPLS or outside of IPv6 addressing. It is sort of its own concept. It is implemented in these technologies using either MPLS labels or IPv6 addresses or address formatted labels, but it is really a completely new technology or completely new layering on top of this old technology. And the most important things, we'll talk about SIDs as a segment identifier, but the most important SIDs we'll talk about are the node SID. You can think of that just simply as the router loopback version of a segment ID. It's the same thing as putting a loopback IPv4 or IPv6 address on your router. And in fact, you often configure it in the same place where you configure the V4 and V6 loopback addresses. So that's where the node SID goes. It basically goes there. The adjacency SID is a label that matches the IGP adjacency that you form, but you can really sort of think of it as the IP address of an interface, a physical interface on a router that is one of your backbone interfaces. That's where the adjacency SID comes into play there. So do a little bit of differences between SR-MPLS and SR-V6. I touched upon this already. We use existing for MPLS. We use existing MPLS labels. You'll hear me refer a lot to things like adjacency labels or node labels. That's because I'm using an SR-MPLS. That's technically wrong. I should be saying adjacency SID or node SID. I will try to keep myself in line, but occasionally I do fall back and just start to say labels a lot. But in the case of SR-V6, it really does look like an IPv6 address. And in fact, the IANA has reserved F500/16 as the IPv6 address space that is set aside to avoid confusion as SR labels. So that means you have 112 bits of label space, as opposed to just your, you know, 20 or 19-bit label space that you use in MPLS. And again, the important thing to remember is these are already existing technologies. MPLS is already existing out there. IPv6 and extension headers already existed, and these are standard extension headers in IPv6. And so essentially, we are taking existing technologies and layering a new technology on top of those and creating use cases out of that. So why did ESnet choose SR-MPLS, particularly over SR-V6? And this is the Michael Lambert question that I alluded to earlier. A number of people have asked this question, both myself and Nick Braulio, who's also, we were both involved in this decision back in the 2016 to 2019 timeframe. And that was prior to the widespread implementation of SR-V6. In particular, vendors weren't really moving fast at that time onto SR-V6 because they didn't really see a huge need for it. And that was kind of the vibe we were getting from vendors, was that they were saying, well, we could implement SR-V6, but there's not a huge demand for that level of label space. Now, it turns out there are other advantages using SR-V6, not just the much larger, that 112-bit label space. And that includes the ability to kind of turn off all of your MPLS protocols. If you wanted to run in a V6 only environment, you could get rid of all of those sort of older MPLS stuff and protocols, and you could just run IPv6. But if you're a network like ESnet, that at least currently in the current time frame and in the time frame that we were getting ready to implement segment routing, we actually already had MPLS running, so it was just a really easy marginal configuration to add segment routing into our existing MPLS cloud, if you will. Like I said, it's on the order of under 10 lines of config just to kind of turn it on and do some stuff with it. So yeah, like a lot of other people, we didn't see the need for the massive space. I think there are other advantages for SR-V6 now, especially now that it has robust implementations out there. But at the time, like I said, we didn't really see the need, and our vendors didn't really see the need, so we didn't have a lot of support for it. And we're writing an RFP. We want vendors to be able to respond to it with, you know, some kind of proposal that's going to be useful. Okay, so given that we're doing SR-MPLS, I'm going to go over a few MPLS concepts here, especially for those of you who, like me, throughout most of my career, my eyes glazed over as soon as I started hearing about MPLS. Again, it had a whole vocabulary that I didn't like. It had like lots of other stuff, lots of other constructs, and it didn't really seem necessary for a lot of reasons for what I was doing, but I've kind of come to see the rationale for doing things with MPLS and obviously with segment routing. So in the case of MPLS, I always ask myself is, you know, if there's something that I don't know much about, but I want to understand the broad concepts in a very, very both useful, but also like not too in the weeds way, I always ask if there's a RAS presentation about it. And RAS is a guy named Richard Steenbergen. If you're in the Nanog community, you've known Richard Steenbergen for many years, probably. But he does a lot of these great presentations. He gives a presentation on traceroute. There's one on optical networking that's fantastic. And there's also one on MPLS where he really gives you a good exposure to the concepts. And I'm going to go through this really quickly. These are obviously Raz's slides here. They're not mine. But MPLS is a mechanism packet encapsulation that sort of is considered to exist somewhere at the layer 2.5 range. So it's above the data link layer, but it is below the IP layer because it actually encapsulates IP packets within it. And so instead of doing what we call hop by hop routing, which is where you look up an IP address at every hop in your network, instead what we do is we look up the IP address once and then slap a label on it. And that label is then what gets switched across the network. If you have a WAN or a regional network or an NREN or some big network, obviously this optimizes the path of the lookups that your packets do as they take a path across the network. So that's great. Why would we do that? Well, in addition to like sort of the basic optimization, you know, the idea was originally that we would basically have routers that would just get so bogged down with all these routing lookups when the internet table became not only classless. So instead of doing like these very simple matches in the class A, B, and C address space, now we're doing longest prefix matches using bitwise prefixes, so like /22s and /19s and all that stuff. Plus, you have the fact that the routing table is much larger. I mean, ESNet's full internet routing table today is probably over almost 1 million routes for IPv4 and over 200,000, maybe in the 260 or 270,000 range for IPv6. So obviously, making router lookups all that time would be very, very consuming, except for the fact that routers nowadays use ASICs, so they don't really have to worry about that as much. In the days that MPLS was being created, all routers were software-based. So like the state of the art at the time was either like Proteons or something like a Cisco 7000 series, where maybe you have other processors, other general purpose processors that are offloading some of the forwarding stuff, but you don't have pure hardware forwarding like in ASICs or FPGAs or things like that. So we don't really need to do it for the optimization as much anymore, but there are a few reasons that we do it. And in addition to the 3 reasons that Raz has here, I'll add a 4th, which is that it actually helps improve network reliability when there's a lot of churn going on or like a big reconvergence event happening in your network. And I'll try to explain that a little bit later on. So Raz gives some definitions. I actually do these also in the next slide. I'm going to use the word LSP a lot in this. And so an LSP is a label switched path. Think of it as an MPLS or segment routed tunnel. And LSP existed prior, obviously, to segment routing. So there are other mechanisms of creating LSPs. And I will tend not to use LERs and LSRs. I'll just use ingress, transit, and egress routers to explain how an MPLS or SR packet is traversing the network. P and PE routers, I've never liked that term, by the way, because it means, it sort of harks back to the commercialization of the internet. I think Steve Wolf is actually on this, and so probably remembers that. But the other reason I don't use P and PE that much is because in a lot of RNE networks, we don't really have P routers. We mostly just have PE routers. So I kind of skip over a lot of that stuff. The advantages of having a P router don't really accrue to us because we don't really configure them not to run routing protocols. All of our routers run routing protocols. So existing MPLS has signaling protocols. You can do static MPLS labels across your network. The only time I've ever done that was in a GNOS class that I took back in the early 2000s. And I got to win a JNCIE study book because I was one of the first people, and these were all RNE people, were the first 2 people who managed to get our packet to go all the way around the little mesh of olives that we had set up in our GNOS training. So basically, the only reason people ever do static MPLS labeling is in a class in order to win a book. They don't ever do it in real life. And in real life, what you do is you have another protocol that creates the sets of labels that your routers will have in their labeling tables so that they can do label switching. In traditional MPLS, those labels are swapped. So basically, a packet comes in with a label on it. The router rips off that label, puts a different label on it, and forwards it out in interface. And the way it does that is all based on what the incoming label and incoming interface are. And so once it goes back out, it's got a different label on it. The next router picks it up, does the same thing. Each router builds its own map of inbound and outbound labels and interfaces, so it knows exactly how to forward packets and can do it very quickly. So the 2 big protocols that are used in MPLS are LDP, the Label Distribution Protocol, which basically builds a shortest path database between all nodes in the network that are participating in MPLS. And the other one is RSVP-TE that involves traffic engineering. I'm not going to talk much about RSVP-TE in this presentation. I'll talk about that more in the next presentation next week. One important feature that MPLS has is you can stack labels. That's used in traditional MPLS mainly for, in some cases, you can do weird things like RSVP or LDP in RSVP, and other things like that. But you can also encode sort of VPN labels. So if you have an L3 VPN, you can encode that label into the label stack that MPLS has. In the case of segment routing, we will actually use label stacking in order to provide a way of doing traffic engineering and creating specific paths through the network. So we do that through label stacking rather than building elaborate labeling maps across the network. I'll skip PHP. PHP is penultimate hopping. It's a lot of implementations use it in classic MPLS, but like the Nokia implementation doesn't do it with segment routing. Just doesn't do PHP that way. It's just, it's not necessary in segment routing to do it that way. So, all right, so that's what MPLS is. And so segment routing over MPLS is different in the sense that it does not do label swapping at every hop. Every label that the packet's going to need in order to get forwarded to its destination is pushed onto the packet when it goes into the network. So the ingress router is the one that programs the packet to do everything it's going to need in order to get to its destination. In some cases, it may only have one label, and that just means take the shortest path to this particular node in the network. In other cases, it may have lots of labels that specify exactly the path that it's supposed to take. Segment routing does not use any kind of secondary protocol like LDP or RSVP-TE. Instead, it integrates directly into the IGP. Now, LDP, the way it works is it actually has some hooks into your IGP, and that's how it builds its map. But it does its own shortest path calculations and its own mapping after it gets all the information from the IGP. And what that means is that LDP can sometimes get out of sync with the IGP, and that can create really bad issues. So it doesn't need to do any of this sort of synchronization with the IGP because it's already in the IGP. And that's a big difference between segment routing and MPLS. The other big difference, of course, is that it doesn't maintain state across the network like RSVP-TE does and OpenFlow also does. And so that's one of the reasons why segment routing, one of the big differences between it, that's one of the reasons why it's kind of liked among network operators. So a couple other things, if you're going to configure segment routing, there are two other concepts you need to know about. So in addition to the sort of two sets of SIDs that I was talking about, the other two things you need to know about are sRGB, the SR global block, and SR-LB, the SR local block. The main prerequisite for configuring segment routing is to create an SR global block. And the reason for that is if you're doing SR-MPLS, you need to tell your router, this is the labels, the set of labels that if you receive these labels, this is segment routing that's running here. It's not classic MPLS. So the idea here is that you can run traditional legacy MPLS and segment routing, and they can all sort of coexist together because you've defined the part of your label stack that is being used for segment routing, or particularly the range of labels that's being used for segment routing. So that's actually very important to be able to do that because it allows you to interoperate all of your segment routing stuff with all of your other things. They can either run as ships in the night, or they can run stitched together as the two protocols literally interoperating with each other. Okay, so a little bit of a sidebar here on how segment routing came about in the community. People essentially wanted to be able to do traffic steering, and that was great. OpenFlow was a good way of doing that, but there were a lot of reasons why people didn't want to use OpenFlow, or at least a few reasons why they didn't want to use OpenFlow. It kind of required a whole new wire format, a whole new set of packets, and a whole new set of things to do in the network. But it really kind of wanted to program the entire network and program state across the network. And so there were some really good things about OpenFlow, but there were also some things about it that I think made it a little harder for network operators to employ at a wide scale. Vendors also, I think, like the idea of we already invested, we already built these really big fancy routers with ASICs and lots of hardware-based forwarding. We don't want to throw that away and just let all of our customers run away and buy cheap white box switches. So let's come up with a technology that takes advantage of all of these expensive features and can actually still like work really well and do all the functionality and the packet programming that our customers want to be able to do. So there's a little bit of a cynical aspect there, and that's why vendors embraced OpenFlow. So, or they did, a lot of vendors did embrace OpenFlow, but they also embraced segment routing so quickly because it was able to like take advantage of really big fancy routers that did really big fancy things, and you just layer this extra thing on top of them, and you can do even bigger and fancier things with them. But there is a certain optimization to that, and that even benefits network operators in the sense that um, you know, the router already understands how to do things like forward packets and stuff like that. You don't need to program all of that in. You don't need to program stuff in from the ground up. As I said in a previous presentation I gave, why didn't I use OpenFlow for traffic engineering? Because I didn't want to reinvent all four wheels of the car I was driving. Let's only reinvent the wheels that we actually need to reinvent here. So this is a guy from Comcast who is talking about why Comcast embraced segment routing. And really the idea here was putting a lot of state in the network was problematic. And instead of programming the network, they wanted to be able to program the packet. And so they were a very early adopter of segment routing. How did ESnet do this? We actually looked at OpenFlow first, and we really wanted to do OpenFlow or some kind of SDN or SD-WAN type of technology. But there were sort of two problems that came up. And one is that if you look at ESNet's topology here, this is sort of the promotional map for ESnet 6. You can kind of see that there's lots of loops in here. So if you want to run this as like a layer 2 network as your underlay and this sort of programmable layer 2 substrate that you can have OpenFlow program all the layer 3 stuff across, that becomes kind of problematic because spanning tree, forget it, not going to happen at that scale. And it turned out that we looked very carefully at Trill and IEEE shortest path bridging. And I kind of understand why those two got into conflicts with each other. And it's not why they tell you they got into conflicts with each other. I can kind of understand why they did now, but I also understand that those technologies were both sort of very difficult to implement at a large scale. Even shortest path bridging, which is more widely supported than Trill, it was still hard in reality to implement. It required you to build a lot of things on an 802.1 Q stack, so you had to do VLAN tagging or Mac and Mac VLAN kind of things. There was just a lot of stuff you had to do in order to make it actually work, and it was really problematic. I was also really interested in pursuing sort of the disaggregated architecture of routing. So instead of having a big router that does everything, you have sort of component routing, like you had a component stereo back in the 70s and 80s. And it turns out that just wouldn't scale. We actually tested it. We tried to run it like, what if we had this router at an Equinix location, or it was connected to Hurricane Electric and it was doing transit and stuff like that. It needed a full internet view. You could do it with IPv4 or IPv6 on a lot of implementations, but not both. And in some cases, BGP just wouldn't converge. It would just get stuck in the middle of somewhere. I think it's still a really promising technology, but it wasn't something that we could really use in the time frame of the ESnet 6. And part of it is just the topology. Part of it also is the fact that if you drill down into that topology, these little dots here actually expand out, and we have multiple links in each between each of our core routers. These are all 400 gig links, and they are all doing ECMP instead of lags. Now, I can get into the decision as to why we do ECMP instead of links. There are a few instead of lags. There are a few reasons we do it, but it's not, that would take too long. So I'm not going to do it right now, but just trust us. There's reasons we do ECMP instead of having lags. So after all of this and trying to get it into our, into the topology that we wanted to do and kind of running through all this, at some point after a vendor meeting, Nick Borrelio just looked at me and said, let's just do segment routing. And so I was really happy because I hadn't thought about segment routing, and I hadn't thought it was, I sort of glazed over whenever, people talked about it. But I felt like this was a really good way of trying to make this technology work. So that's how we got the ESnet architecture we have now. The layer 2.5 MPLS, that's really layer 2.5 is SR-MPLS that's sitting there. And that's kind of like what we decided to implement. So given that we're doing SR-MPLS, one of the things that I talk about SR just integrating directly into the IGP. So I should talk about what IGP ESnet runs, and we do run ISIS. ISIS is great because it's very extensible. I mean, essentially it has to be, since the protocols that ISIS was originally developed for, nobody in the world uses. So of course you had to be extensible to be able to use protocols that, be able to route protocols that people actually use. And it allows you to embed segment routing information into its basic protocol units of TLVs. So there are different ways that there are different sets of TLVs that advertise different aspects of the segment routing, like things like node SIDs, adjacency SIDs, prefix SIDs, and a bunch of other things. So it actually makes a lot of sense. If you're running ISIS, segment routing is a no-brainer to turn on. It's really easy to do. Now, you might be asking yourself, why are you running things like IBGP and EBGP and ISIS? Well, maybe you can understand why we're running EBGP, but why IBGP and ISIS? So in any WAN context, BGP is used to exchange external routes. And it's important to understand that external route is very broadly defined in a WAN. Basically, anything that's not on the backbone or in like the immediate management plane network, those are considered external routes. So even ESNet's perf services, those are considered external routes from the perspective of the ESnet. So if you're going to an ESnet perf node, you're actually going through a route that's being redistributed in BGP throughout the ESnet network. And so it's important to be able to have another protocol running under IBGP that kind of gives a little bit more information as to how you reach stuff within the network. And the reason for that is that IBGP provides a next hop that is a router loopback. Okay, so that's really useful. That tells me, okay, I need to go to this router to get to this external peer. Like say I'm going to Cloudflare. I need to go to my router at Equinix Chicago or Equinix Ashburn, one of those locations. But it doesn't tell me how to actually get to that router if I'm not already that router. So there needs to be another mechanism for providing the shortest path through my network so I can optimize my traffic. It also provides a tiebreaker if I have cases where I have multiple EBGP routes or IBGP routes through the network. So for example, I may have 4 or 5 peerings with Cloudflare, 4 or 5 peerings with Google. I know we have, I think, 5 or 6 peerings with Internet 2. So Internet 2 and ESnet have 5 or 6 interconnection points. You want to try to find the one that's closest to you, or maybe you don't. Maybe you want to keep that route on your network as long as possible. But in order to figure those sorts of things out, whatever those policies are that you run, you need to have a way of saying, how do I get to this location in the way I've decided to optimize it? And that's why you run an IGP, even in a place where you're running lots of BGP all over the place. Now, remember that IBGP provides the next hop of an external route given a router loopback. And in order to get to that router loopback, that process I mentioned is what the IGP does, but it is also called next hop resolution. And I'm going to talk a lot about that because the first use case we're going to have for segment routing is we're going to configure it for our next hop resolution. In other words, instead of using just hop by hop IGP routes to get from one location to another, we're actually going to resolve it into a segment routed SID and just throw that through the network and switch it very quickly to get to the location we want to go. So next hop resolution is our first use case. And so that means that we should understand how WANs and regional networks, and maybe even your network, how we do next hop resolution for our external routes. The simplest form, of course, is what we call hop by hop over the IGP. I should say not necessarily simple. It's both simple and complex. here is what a router would actually say if it were doing that. And again, I'm using Cloudflare as an example. It has to do a lookup every time. So every router in your path has to do a lookup against its full internet table. Now, again, if you're a really small network, maybe you only have like 2 or 4 or 5 routers that have full internet tables, or maybe some of them have partial internet tables, and you may not have to do this as much. But in a large scale network, or in a network that goes over the wide area, or a regional network, that's kind of a lot. You have to do this over and over again. But more importantly, there's another problem, which is, what if these 3 routers that we're going through, the ingress and egress, particularly this middle router, what if it disagrees with another router in terms of where the shortest location is? And the cases where it may disagree are instances where you might be in the middle of a convergence event, like one of your Cloudflare peerings just went down and not all the routers have updated their routing tables. So what would happen in that situation is you would get into routing loops, which for just maybe a few seconds, or maybe upwards of minutes, if it's a very large peer, like level 3 Lumen, whatever it is today, what goes down, or Hurricane Electric, one of your Hurricane Electric peerings goes down, you have a very large reconvergence event happening, and that has to propagate all across your network if you're running IBGP. So this becomes problematic for us, particularly as a WAN, if you have to do these lookups from scratch at every hop, because it means you can end up with routing loops. And actually, not could, we will end up with routing loops in situations where we're doing hop-by-hop routing. We've proven it. The other mechanism is to do MPLS with LDP, a more traditional protocol, and that actually fixes the problem that I just talked about with the hop-by-hop routing, and it makes it a lot easier, but it does require you to run an extra protocol, and that protocol has to be in synchronization with your IGP. It's not absolutely horrific if you're just using it for next hop resolution, but you can still get into situations where you have routing loops if the LDP and the IGP aren't in sync. So then that's why we go to the third one, which is basically SR-ISIS, which is we integrate segment routing into the IGP. And in addition to advertising router loopbacks and building shortest paths to get to router loopbacks, alongside those router loopbacks, we also advertise the node SID of the router. So we advertise a segment routed identifier, which identifies that node SID. That, again, remember, that's the equivalent of the router loopback. And so when we do that, that allows us to do a really quick forward. We just push one label. We don't have to do any label swaps, and we don't have to worry about LDP and IGP synchronization. So it's the most efficient way to forward a packet across the network where we're doing next hop resolution of external routes. These slides will be available, by the way, so you can read this later, so you don't have to listen to me talk through it the whole time. Okay, so this is sort of like, I just sort of gave you the advantages of doing this, and it allows, like, really the most important thing is that you can do stateless packet programming, and you don't have to worry about synchronization of other protocols with your IGP. So it just makes it very easy. It's also really easy to configure. So in the case of ESnet, first thing we had to decide on is where we put our sRGB. We use the label space between 400,000 and 500,000. That's in the MPLS label space. That gives us 10,001 labels. I call that Boralio math because Nick was the one who specified that range. But because we're including both ends of it, we have 10,001 label, or 100,001 labels. And for various reasons, the node SIDs are indexed. So when you configure them, you only configure the last 5 digits of the node SID, and then you add that onto the base of your sRGB. That's done so you could renumber your sRGB really easily by just reconfiguring that thing and not having to reconfigure every one of your routers. So that just makes it a little easier. If you're switching vendors and they have different reserved label spaces and you want to renumber, you can do that pretty easily. But that's really the only reason you do that. And so far, we haven't had to do that. So we actually have an internal network database where we keep track of the node SIDs. This is really a little bit of a misnomer. This is not actually the node SID, it's the node SID index. The node SID itself when it's converted into an MPLS label, it actually has a 4 in front of it here. But here's an example of a router located as part of the FRID project at Michigan State. And that, in addition to having lots of other information about the router, we do maintain the information about the segment routed node SIDs in there. And this is how you actually configure it on a Nokia. This interface system, this is how you configure the loopback address. So in this configuration, in addition to having these 2 node SIDs, and I'm just making these numbers up, this is in our lab, but in this location is where you also configure, again, the router loopback v4 and v6 addresses as well. So it just fits right in with that configuration. It's really easy to do. In terms of adjacency SIDs, I'm going to talk about that in the next talk when we talk about traffic engineering. So I'm going to mostly gloss over it now. But it also is useful as you're setting up segment routing. If you want to do static adjacency SIDs, you do want to configure an SR-LB. And why you want to configure static adjacency SIDs actually will come in the next talk. That's on January 31st. Just keep plugging for my next talk here. We'll leave you with some cliffhangers then. Okay, so in that case, the only other thing I need to do in order to turn on SR-MPLS is set aside the label space and then put it in my IGP that I'm going to start doing segment routing. And I don't even need to do the SR-LB stuff, as I mentioned. I'm not doing traffic engineering till next week. So for this week, all I need to do is really this line of config and the lines of config that are below. There's one other thing I'm going to do, and I'll explain that later. Once I do that, as soon as I enter those commands that I just entered and configure my node SIDs on each of my routers, my node SID indexes, then what happens is my Nokia router, in the case of Nokia, will build a tunnel table. And that tunnel table has all of the sort of underlay tunnels that are used to apply other services, L2 VPNs and L3 VPNs, and even basic next hop resolution. If you think about, if you're familiar with Junos, that's very similar to table inet.3 or inet 6.3. So it has a very similar function and sort of similarly managed, except that I don't know about new versions of Junos. At least in older versions of Junos, the route preference was sort of guiding whether or not inet 3 would actually come into play. In the case of Nokia, the tunnel table has its own set of preferences. So it's managed the same way as a router preference in the sense that the lower number actually wins. But that is separate from the route table preference. But you can think of it as a similar concept as routing preference or administrative distance, as Cisco calls it. And in this, here's an example of the tunnel table with no heading, so you can't really know what any of these things are. But the thing on the left, these are all router loopback addresses, and these are the different types of tunnels that it will take. Now, you can see here in ESnet, this is a real tunnel table on a real router. This is located at Lawrence Berkeley Lab. And this router has both LDP and ISIS. The ISIS ones, those are actually segment routed tunnels. So, and then it also has other things like RSVP. Those are used for L2 VPNs. We don't use those for any of our layer 3 services at this time. But you can see how ISIS or SR-ISIS, it should be, I don't know why they just say ISIS, SR-ISIS and LDP coexist. And the way we mediate between the two of them is by having different tunnel table preferences. So you can see here I've set the tunnel table preference to 11 for SR-ISIS. That means I'm preferring it over LDP, which is set to 15. Okay, so I've configured it now, and what I want to do is I want to turn on next hop resolution with these segment routed tunnels to get all those advantages that I just talked about. But there's another advantage that I want to use, and you can remember in that RAS presentation that I showed you with those other slides, he talks about doing fast reroute as another mechanism for why you might want to use MPLS, another use case for MPLS. And what fast reroute allows you to do is it allows you to take a separate path for a packet to immediately fail over to a different path, even before your IGP has reconverged. So it gives you like really good, really fast failover. So there's a version of that, an even easier and faster version of that that runs with segment routing, and that's called TI-LFA, or topology independent loop-free alternate. It's a mouthful. I'm sorry about that. Even saying the acronym is a mouthful. That's what they came up with. But really what it does is very simple. It looks in the IGP because that's what we do for segment routing. We're always looking at the IGP. It looks at the IGP and it says, what's the second best path given a particular failure mode that I can tweak a little bit? Like, for example, if the router next to me goes down, what's the second best path I can take to get to another location before the IGP is reconverged? So it gives you that idea of being able to quickly switch to a different path without having to worry about waiting for your IGP to reconverge. So let's go and configure it, and I'll show you what it looks like when you've actually configured it and what it means. Again, it's really easy. It's just like a line of config basically here. Again, we're configuring it in Nokia. We configure it in our IGP. And what this means is I'm going to allocate 2 labels. So basically in the SR-MPLS stack, 2 labels will be used for being able to do TI-LFA. The more labels you use, the more failure modes you can basically work around. But it also means that you are consuming more labels in the MPLS label stack, which is limited in MPLS. It's limited both because of hardware ASICs and in some cases because of the packet format. It may also be limited. So in the case of Nokia, we're limited to about 12 labels, but because some of those labels are used for other things, it really gets us down to about 9 labels that we can actually use for all of our label stacking. This will come into play when we talk about traffic engineering next week, again, giving a plug for that talk. So once we configure it, we're saying, you know, I want to get like around like 80% or 90% of my failure modes. And it's not that those failure modes won't eventually fail over. It's that I want to have this really fast reroute mechanism with 80 to 90% of my failure modes. And I can do that with basically 2 labels. Okay, so that's kind of a happy medium. If I did 3 labels, I could get more failure modes, but again, you know, it's a way of like conserving label stack depth. Okay. And then I also do node protect here. And again, this is sort of a trade-off because we have so much ECMP in ESnet, and ECMP and TI-LFA are sort of mutually exclusive, because if a link goes down in ECMP, you just hash over to your other links. But if a node goes down, you want to be able to route around that node. So that's actually kind of important. So here's an example where we don't really have much TI-LFA going on because this is, again, this is a backbone router that has 3 backbone links. So there's not really a use case for being able to kind of route around those link failures. If we did go to 3 labels, we would actually get some LFA in this particular router, but I'm not going to go into that just yet. I'm still experimenting with that in ESnet as well. But here's a router. This is located at a smaller site, and this smaller site has 2 routers and then just an uplink on each router. And so in this particular location, I have available LFA routes. That's what the parentheses L or bracket L means here. And so this is what it looks like when I do that. So here you can see, here's the primary path. It just has a node SID. And so it just says take the shortest path to this node SID. But the backup path, assuming the IGP hasn't reconverged yet, actually has 3 labels, which are, you read in reverse order here, basically. It says first go to Equinix Chicago. This, I'm trying to get from basically Savannah River over to Atlanta, essentially, to get to Washington, D.C. So here I'm saying this is the link to Atlanta, and it says instead go to Equinix Chicago and then take this other link and then go to Washington from there. And I take a different exit from my router that just goes to another backup router. So that's how LFA works. And this is programmed into the ASIC. This FP tunnel table means it's programmed into the chipsets. So I actually pre-programmed that in so it can fail over really quickly. So once I've done that, what I'm going to do now is actually take advantage of all of that and configure it for my next hop resolution. And so I'm going to do this by saying, let me for each address family, I want to use these sets of tunnels, these types of tunnel protocols. In this particular case, I'm only really interested in SR-ISIS. This is actually a live configuration in ESnet. So I do have a bunch of different tunnel types that I use, but I just want to make sure that SR-ISIS is allowed. And the reason the word resolution filter is repeated here is because you can also do resolution any, which ignores the resolution filter. I'm telling it, go ahead and look at the filter that's right here in terms of doing your next hop resolution. In an L3 VPN, which most of our traffic is actually in, this is our main IP transit VPN 293. It's also done using this autobind tunnel mechanism. What autobind tunnel does is it doesn't go per address family. So it actually turns out that all of our IPv6 traffic is essentially encapsulated into IPv4 signaled MPLS label stacks. And we're working on trying to get that reversed. Okay. So I'll talk about that in a little bit. So what does this look like once a network implements it? Now, in this case, I'm actually looking at an NL-nog ring node over at SurfNet, and I'm doing a traceroute minus here. In this case, I'm doing MTR, and you can do some tricks here with it. And this is what I wanted to show you. If you're not even on a network that's running segment routing, but you want to try to troubleshoot what's going on, or you want to just try to see how your path is taking, you can kind of figure that out by running obviously traceroute, but there's some flags to traceroute and other traceroute programs like MTR that allow you to see the MPLS labels for networks that are exposing their MPLS labels. And in this case, it's going over SurfNet, which you can see they're running some form of MPLS here, and they have a label on it. In the case of Internet 2, as we get over Internet 2, and that IN is the beginning of Internet 2. So we're going over Internet 2 here. And then I'm going, I think, to ultralights. I'm going to Caltech. So I'm going from SurfNet in the Netherlands to Caltech here. And basically, the question for everyone is this, do you think they're running segment routing here over MPLS, or are they running something else like LDP or RSVP? Any show of hands, who thinks they're running segment routing? Just do a little emoji, like a check mark emoji, or say, and if you think they're running LDP, you could do like a thumbs down or something like that. Yeah, it turns out they're doing segment routing here. At least we can infer they're doing segment routing here because you can see the label, the first label in the stack doesn't change. Okay, so all the way through the labels, it's this 16022. The second label in the stack, that's most likely an L3 VPN label. So that's used to talk about what L3 VPN or VRF that this particular packet is going to. And that is something that is sort of per router. I'll show you how that works in ESnet in a second, but that gives you an idea. Now, in this particular case, where we have something that's going over ESnet, is this doing segment routing or LDP here, or something else, maybe RSVP? How many people think segment routing? And put your thumbs down if you don't think it's segment routing now. Nobody doing any emojis here. So yeah, it turns out this is LDP, right? Because we're seeing the label swaps happen at each one. Now, a couple other things to understand. Why are these other labels here? In this particular case, label 7. What that means is the label that follows is a random label. Why do we put random labels in our MPLS stack? It's done for ECMP. It actually allows you to just hash your ECMP routes based on the label stack rather than being based on other things like IPv4 and IPv6 address. It's an optimization that lets you look at only the label stack rather than having to look into the packet to try to see if there's anything else I can hash against. So this way, I'm putting some random stuff on my labels here so that, or on my label stack, so that I do better hashing across ECMP links. And we've proven that this actually really works really well. And if you don't do it, then you get problems. So I can show you information about that if you're interested later. And so this is actually what it looks like if you actually look at a NetFlow packet. Now I'm using, in this case, Wireshark to decode NetFlow. But if you don't have access to NetFlow, obviously you can't do that. But here again, you can see NetFlow actually knows that this is an LDP packet. And you can see that it's in our LDP label stack, and then there's the entropy label. So you can kind of see this in this case. Why is this LDP? It turns out that in our GRT, our global routing table, we still use LDP for forwarding IPv6, and the reason for that has to do with the way Nokia supports segment routing in multi-topology ISIS. They weren't doing it until very recently, and we're not currently running an operating system that lets us do that, a version of the operating system that lets us do that. So that's kind of why. Okay, so here's an example through ESnet of something, and again, I'll ask the question, but I think you already know the answer. Is this running segment routing, or is it running LDP here? And the answer is, well, look at the first labels. They don't change throughout the whole path here. So this is pretty clearly segment routing. Again, we have our entropy labels, and then you see this one down here, the bottom label of the stack, that is 524.081. That's actually our VPRN label. And that's based on a per router thing. So here's a different packet going to a different router that again has a VPRN label on it. You can see there's the segment routed label. The top label type, it says is unknown. This version of NetFlow doesn't know what kind of label type that is. And then you've got your entropy label, and there's your VPRN label. And here you can see the actual route, and you can see that the route as it's distributed in IBGP actually has a VPN label stuck on it. So that's the same VPN label you saw here. And that label, it turns out, matches the node SID you can see the node SID that it's going to here, 426.100. That actually matches the node SID 261.0.0 of BNL 515. So that's our shard router at BNL. Here's a teaser for next week. Here's one that has two what appear to be node SIDs on. What are we doing there? Why is that happening? Well, that has to do with traffic engineering. We're going to talk about that next week. So just by using our TRS-80 Model 1 with cassette drive version of segment routing, we've been able to improve the resiliency and efficiency of our network. We've been able to eliminate, in many respects, chances of routing loops that happen during reconvergence events. And we've been able to simplify the actual routing lookup process and even make troubleshooting a little bit easier, because when I look at these sort of trace routes here, I can say, oh yeah, this is clearly going to a particular node that I can, I can resolve that to a particular node, or I can just infer it. Like I can infer from the Internet 2 one, I don't know what their node numbering is, but I can infer that maybe the Los Angeles router has 160.22 as its node SID. So I can do a lot of stuff that makes troubleshooting easier by using segment routing and by using it for this next top resolution process. And so in terms of more sophisticated stuff, once we want to add like a floppy disk to our TRS-80, once we want to add the expansion interface and maybe, I don't know, maybe upgrade it to an Apple II maybe, we can talk more about how we do that with traffic engineering. We'll talk about that next time.
Thank you, Michael, very much. And I was very much in the Commodore VIC-20 camp myself, but TRS-80s are great. I think we have time for one question or so, and of course, everyone's going to be excited about next week. So, John, or I have a question from John Graham. Can we combine SR-V6? Question. Yeah, right. Sorry, you can read it there. On the I can't read it myself because I don't have my glasses on. On the edge with SR-MPLS in the core.
I believe, well, you can, except that the packet format's going to be different. So you can run them both in your core, but you can't put them, I don't believe you can put them in the same packet. Okay, so in the sense of, yeah, you can run both of them, but you don't have to. And in terms of the next question was SR-V6 considered, I believe that is answered in one of my slides back here. Nick also just answered it, but there were two reasons. And I can't remember where it is, but no, it's in here. So Maybe it's a great Easter egg for you. You can go ahead and find it
There you go.
where it is.
All right. Well, to be continued next week. Thank you, Michael Sinatra. That was really interesting. And thank you all. We've recorded this and we'll get this up and other recording up for folks who want to rewatch it. And of course, we'll be continuing next week.
And feel free to drop me a line, ms@es.net, if you have any questions.
Thanks all. Have a great weekend.